with chapter 6 and kind of continue on at that point and kind of see what we get to. And like I said, the other previous chapters to chapter 6 kind of going in the order that we went already up there on Canvas for you to look over. All right, so we'll start with what was in chapter 6. So really, chapter 6 was about equations. And obviously in chapter 6, we talked about the idea of proper equations. So we always start with our reactants that go to our products. Reactants obviously being our starting material, and products are obviously the stuff that are formed. In an equation, as we've talked about, there's many different sort of symbols that we see. We have solid, liquid, we have the gas state, we also have the aqueous state. There are sometimes written underneath it. In addition, on top of the arrow, a lot of times catalysts are basically written there. Remember, a catalyst is something that speeds up a chemical reaction. It is not a reactant. And it's not a product, and it really does not get used up in the reaction. It is there really just to facilitate that reaction happening quicker, as we talked about in an earlier chapter when we talked about energy. Really, the way it's able to do that is from reactants to products. There's this activation energy, which is the energy hill that the reactants has to climb basically to get to the other side. So a catalyst can find an alternative pathway for that reaction to take place, a really more efficient way for that reaction to take place. And what it ultimately does is actually will lower the activation energy. So it lowers that hill that the reactants have to climb, and that usually results in an increase in the rate of the reaction that takes place. Most importantly, what we talked about really in this chapter was the idea of we should balance equations. And obviously, hopefully at this point, we know how to balance equations. But remember a couple of things. They do need to, it's always the coefficient is the only thing that we change. So again, it is only, so it's only the number in front that we change. We never change anything else. And when you are balanced, you need to make sure, obviously, two things. They're all whole numbers, and that they are the simplest set of whole numbers. So a reminder, if you did balance something where we'll just say, for example, again, that this is balanced with these coefficients, because you can't go through and divide everybody by 2 and still achieve whole numbers. That is really what you should do for the properly balanced equation. The other thing that we also talked about was just a couple of tricks to balancing, right? You can definitely use a fraction if you need to, but you do need to clear the fraction along the way. You do have to use a fraction sometimes when you do have a sort of diatomic element by itself on one side and that element and multiple things on the other side is sometimes when that occurs. The other thing that we talked about in terms of balancing was pretty straightforward. If you have polyatomic ions, sometimes it's much easier to keep those guys together as you're balancing, and rather than kind of go element for element and kind of balance them as kind of whole units. And that usually allows things to sort of fall into place. Any questions on chapter 6? Wasn't much in that chapter other than balancing, I think. Then we sort of took this to chapter 7, and we talked about different types of reactions in chapter 7. Chapter 7 was really types of reactions. And if you remember, really reactions can be broken up into 2 big sort of categories of reactions. One are double displacement reactions. And in a double displacement reaction, This is the general setup, and how you know you have a double displacement reaction is you really have two ionic compounds that are coming together. Whenever you have two ionic compounds that are coming together, it is always going to be the two positive guys that will switch partners in this case. This will result in two new ionic compounds being formed. And as a result of this type of reaction, there's really two more specific ways. And see how many times I can say really in the same sentence. There's two more specific ways that you could classify these type of reactions. A lot of times in these type of reactions, you will end up with a solid that forms, which is sometimes referred to as a precipitate or a PPT. And in that type of reaction, when a solid forms, that means that we have what is referred to sometimes as a precipitation reaction. So a precipitation reaction really is a double displacement reaction when a solid forms, but a more specific classification for it is obviously a precipitation reaction. The other sort of thing that falls under the double displacement umbrella is perhaps you make water over here. So maybe one of these guys makes water. And if it makes water, oftentimes that happens in an acid-base neutralization reaction. Like HCl plus a little sodium hydroxide makes some water and sodium chloride. Remember, when you take an acid plus a base, you usually will get water and a salt. And the formation here of water is another very common double displacement reaction. So acid-base neutralization reaction falls under the big umbrella of double displacement reactions. So does precipitation reactions. How do we know if we get a precipitate? We also talked about in this chapter, solubility rules. And remember that you can use solubility rules to help you determine whether or not something will make a solid or not. Just some of the rules to remember, or some of the ones that we talked about. Anybody in group 1 is soluble. Things that have nitrate are soluble. Things that have acetate are also soluble. Chloride, bromide, for example, and iodide are soluble. But remember, there are some that do have exceptions, and this would be one of the ones that do have exceptions, like lead, mercury, and silver would be the exceptions. And remember that if it happens to be an exception, basically the opposite occurs. So you would expect really a solid to form in this case. So there's obviously a couple of slides there in the notes and stuff that go over all the rest of the solubility rules. So I won't write them all up here. But we could use these to help us determine, if we do put these ions together, would we expect a solid to form? In this type of reaction, it's very common that we also can display what is going on in 3 different types of equations that we talked about. For example, the molecular equation, the total ionic equation, and the net ionic equation. So for example, if we use something like our solubility rules, when we take something, say, like sodium chloride plus a little silver nitrate. Again, when we look at this here, this is a positive, negative guy, positive, negative guy. So if I was not sure of what's going on, that should tell me that it's a double displacement reaction, which means, again, here, our positive guys will switch partners. So these 2 guys are going to switch. And that would give us some sodium nitrate on this side and a little silver chloride. So when we look at this, we can use our solubility rules. For example, we see sodium, so that's always soluble. So we know it will get the aqueous symbol. We see nitrate, which is always soluble. There's no exceptions. So it would also get the aqueous symbol. Here, you can look at either one of these and they would tell you that it's going to be aqueous. This is chloride, which is soluble in everybody except for silver, which again would be an exception. So that means it would then become insoluble, and that would be a solid. This would give us our balanced equation. Since it is balanced, we don't need to put any coefficients in there. And this is obviously our molecular equation. And remember that once you have your molecular equation, anything that is a strong electrolyte will 100% break apart. Anything that's a weak electrolyte will stay together mostly, but break apart a little bit. And anything that's a non-electrolyte obviously will stay together. So in this case, sodium chloride is a strong electrolyte, so it will completely break apart into its ions. The silver nitrate also going to break apart. The sodium nitrate will break apart. And remember that when you write this type of equation, anything that is a solid, a liquid, a gas, or a weak electrolyte, you would keep together. So in this case, we would keep together the silver chloride as it is a solid. This is what is sometimes referred to as the total ionic equation, or complete ionic equation, sometimes people call it. When we look at this equation, we can find ions on both sides of the arrow, which look exactly alike. So we got some nitrate, we got some sodium. These guys here are what are referred to as spectator ions. So all the guys in the blue circles are spectator ions. They are there really just to balance out the charge, but they are not really there to form the actual product that's being made. We typically cross those guys out in our total ionic equation. And that leaves us our last type of equation we talked about, which is our net ionic equation, which would be our silver ion plus our chloride ion is making the silver chloride. So this is really, the sort of the reaction that's taking place. In this particular situation, it's really that formation of that solid is what we see here. Any questions on those sort of equations? Remember as well that when you are predicting this side of the equation, you want to make sure you start with the correct formulas first and then balance it so you don't get any really funky formulas that you shouldn't have. Also, for example, if we had say something like this, and you're going to break it apart into your total ionic equation, this guy would break apart into a calcium ion and 2 nitrate ions. So that 2 comes to the front when you do it. Also, if you had, say, a 2 in front of somebody in there, the 2 also gets distributed to everybody as well. So if you were to break it up into the total ionic equation, that 2 would also be distributed to everybody as well. So don't forget about those coefficients if you should have some. That's why it's really important to make sure that the first guy is balanced, because if you balance that, then everything else should be completely balanced. And that means when you do get to your spectator ion part, like we talked about, those guys should definitely completely cancel out, and you shouldn't have unequal numbers of spectator ions. Any questions on those equations? Remember that there's really 3 reasons why a reaction takes place, which are sometimes referred to as the sort of 3 driving forces for a reaction. And that is the formation of a solid, the formation of water, and an electron transfer. And really, double displacement reactions pretty much take care of those first 2 reasons why a reaction takes place. The other reason electron transfer happens in what we talked about, which was redox reactions. So redox reactions are the other sort of big category of reactions, and it's sort of the big umbrella for which they fall upon. Redox reaction stands for oxidation and reduction reactions, and we had some definitions of each of these guys. When something is going through oxidation, it means it will lose electrons, and when something goes through reductions, it will gain electrons. So there's sort of a simple way to figure out if something's being oxidized or reduced that we talked about. You could just use a basic number line And if the what is really referred to as the oxidation state, but if you want to refer to it as the charge for this class, if the charge or oxidation state from the reactants to the products for a particular element gets more positive, that means it is losing electrons and going through oxidation. If you look from reactions to product and that element's oxidation state is getting more negative, that means that it is gaining electrons and going through reduction. So if we had, something like this, for example, and we end up with, actually, no, that's a very bad example. Well, I may not do that example. Take 2 on the bad example. Let's try this again. Let's try a better one. Let's try this example here. There we go. So if we look at something like this and we throw a little balancing action in there, which would be probably the right thing to do, would look something like that. So we really can look at the oxidation states of everybody. And I think we talked a little bit about oxidation states in sort of a quick way to be able to assign them. If we look at this, anything that again is pretty much by itself in its natural state, uncombined, really has an oxidation state of 0. So the zinc has not attached to anybody or anything like that. So that's going to be 0. This is hydrochloric acid, which is really the hydrogen being +1, chloride being -1. When we go to the right-hand side, the zinc now is zinc chloride, and it is ionic because it's attached there to the chloride, which now makes it a +2 charge. The zinc is -1. And hydrogen, that is how hydrogen normally comes in its natural state as hydrogen gas, so it's 0. So we can look at this and actually figure out what is happening in terms of oxidation and reduction. If we started with the zinc, it started at 0. And it ended over here on the right-hand side at +2, which means it's becoming more positive. So the zinc here is going through oxidation. If we look at the hydrogen here, the hydrogen on the left-hand side is starting at +1, which would be like here. And on the right-hand side there, it's ending at 0, which means it's moving in this direction, becoming more negative. And that means it's actually the hydrogen here that is going through reduction. The chloride on the left is -1. Chloride on the right is -1, which means there's nothing happening with the chloride in this particular case. Any questions on that there? This equation that I wrote is a molecular equation. You could actually write a total ionic equation for this type of reaction as well. The zinc here obviously would stay together. Hydrochloric acid is a strong electrolyte, which means it would break apart into H+ and 2 chlorides. The zinc chloride here would break apart into zinc with a +2 charge and 2 chlorides as the 2 comes in front. And our gas would obviously stay together in this case. When we look at this, we see that we actually only have one spectator ion, which is the chloride, which is the guy that's not changing in terms of its charge. And if we cancel that out from our total ionic equation, we are left with the net ionic equation of what's happening here in this redox reaction, which is basically the zinc here is going to toss over a couple of electrons, and the hydrogen is going to accept both of those electrons. Is really what's happening. Zinc going from 0 to +2, hydrogen going from +1 to 0 being oxidized. So this is a net ionic equation here. Questions on any of that there? So this big part, our type of reaction, has a lot of individual sort of more specific classifications. clearly redox reactions handles the transfer of electrons part of what's going on. But a reminder that these things always occur together, which means if there is something that is being oxidized, there is something that's being reduced at the exact same time. So the good news is if you can just figure out one, by default, the other guy has to be doing the opposite thing. So that's sometimes a good thing. Maybe you can only figure out one of them. So under this sort of classification of reactions, we have a bunch of individual sort of classifications. We have our combination, our synthesis reaction, and that is when two things basically make one thing, right? Putting it together. We have our decomposition reaction, where we have one thing makes multiple things, so sort of the opposite, breaking it apart. We have the reaction like we just saw there, which was referred to as a single replacement reaction. And that is when you have one thing that comes in and replaces something else. So if this is a metal, it will come in and replace the positive guy and make one new ionic compound, and the guy that comes off will have no charge. Remember that you could also do this with nonmetals. So if this guy here was a nonmetal, it would actually come in and replace the negative guy in this case. And to do that, it will then make a new ionic compound, and this guy would come off as well. So remember, they both could do that. Also remember, in order for this reaction to take place, the one coming in has to be more reactive than the one it's replacing. So whatever is coming in needs to be more reactive than what it is replacing. Obviously, if it is not more reactive, then the reaction would not take place. So you wouldn't get a reaction that would take place. So for example, the one I just did there with the zinc and the hydrochloric acid, if you swap out zinc for copper, copper is less reactive than hydrogen, so it will not take place. One thing that you could use to help you determine, will a reaction take place is sometimes they have what are referred to as an activity series of like metals. Usually on this, it's just a list, and then hydrogen's in the middle, and anybody that's above hydrogen, so anybody's below. So anybody higher on the list will replace anybody lower, and vice versa. Anybody lower on the list will not replace anybody higher. So if you ever see an activity series, kind of looks like that. So our example there, you would see zinc higher on the list, and you would see copper kind of lower on the list. So copper would not replace hydrogen in that particular case. Another one that falls really under the redox umbrella is a combustion reaction. And there are really two types of combustion reactions that most people think about. Really, your basic definition of combustion is, frankly, you just need oxygen to be present. So just the presence of oxygen is technically considered a combustion reaction. But most people, when they think about a combustion reaction, oftentimes think about the organic combustion reaction. And that is some type of organic compound, which usually contains carbons, hydrogens, and oxygens, plus some O2, makes some CO2 plus water. So I would say probably 9 times out of 10, somebody's talking combustion, that's probably the one they're talking about. But technically speaking, really anything with oxygen is considered a combustion reaction. That is why, as we went through this chapter, we did talk about, there's a lot of different ways that you can maybe classify the same reaction. If you had something like this here, this is a combination. That's two things that make one, right? So you could call that a combo reaction. This is also a combustion reaction because technically speaking, it has oxygen. And you could also classify this obviously as a redox reaction because there's basically a change in electrons that are happening as well. So, you know, there's multiple ways you could sometimes classify the same reaction. One kind of choose the best one that obviously makes the most sense. Any questions on how to classify reactions there? All right, so let's see here. That was 7, which I think was all that. All right, so I think that was the majority there of chapter 7. Then we went into chapter 9 after that. So chapter 9 was really about stoichiometry. So really this chapter was the big stoichiometry chapter, which obviously is an important part of what we talked about. So stoichiometry really did tie together kind of the couple of chapters that came before it. Again, before it, we talked about moles, right? And we also talked about, obviously, types of reactions and equations. So this chapter put both of those things together. And we have really kind of 2 different types of stoichiometry problems that we talked about in this chapter. One is really a basic stoichiometry problem. And remember that in stoichiometry, we use the balanced equation to basically come up with conversions. So we could take all the coefficients here from the balanced equation, and we could say in this example that 2 moles of A reacts with 3 moles of B. 2 moles of A gives us 4 moles of AB. 3 moles of B gives us 4 moles of AB. So these are all the equivalents that we could get from the equation. Any of these, we could write 2 conversion factors to work these problems out. You obviously would not use both of them in the same problem. You would pick the one that you need. And really, the purpose of stoichiometry is you're really given information about somebody in the equation, but you're not actually interested in that person. So you do need a way to go from like a reactant to a product to a reactant to another reactant, or a product to another product. You need a way to kind of move through the equation, and using these coefficients as the moles is the way that allows us to do that. There's really 4 basic steps to all stoichiometry problems, really basic ones. Always starts with the balancing of the equation. If you are not starting with a balanced equation, then you will definitely have the wrong relationship, and that's no good. You want to take whatever they give you, basically, and convert it to moles. And in a basic stoichiometry problem, a lot of times you're given things in grams, so we would use the molar mass from the periodic table and divide to get to moles. So this would be the molar mass in grams per mole from the periodic table. And once you have it for moles, you then want to find the mole to mole relationship. And the mole to mole relationship you're looking for is from the balanced equation. And once you do that, that will convert you really from what you're not interested in to what you are interested in. The last step is you should always be in moles at this point. You may want to convert it to some other unit. And a lot of times here, we will also use molar mass, or the opposite way, by multiplying by the molar mass to figure out how many grams we may be produced. When you do this basic sort of stoichiometry problem and you figure out how much product you would produce based on how much reactants you started with, that is what is known as the theoretical yield, right? When you do the calculation from the equation and you figure out how much product that you would produce. When you're doing stoichiometry or basic stoichiometry problems, or really any stoichiometry problem, it doesn't always have to go kind of from reactants to products or products to reactants. You can't stay on the same side of the equation. So you can do relationships with stoichiometry between two reactants, between the two products, from a reactant to a product, from a product to a reactant. So you can use stoichiometry for really the relationship for everybody that is in the equation. Any questions on that there? Now, there was sort of a different type of calculation or a similar type of calculation that occurs when we do stoichiometry, and that is when we have what are referred to as limiting reagents or limiting reactants. In most sort of reactions, there's always a reagent that gets used up first. And that is what is known as the limiting reagent or reactant. And there's a reagent that you have plenty of and left over at the end of the reaction. That is what is known as the excess reagent. Now, there are multiple ways that you can kind of solve these problems, but I believe the approach that we took was if we did have an equation like this. And let's just say we started with 5 moles of this guy here and 2 moles of this guy here. You know, we want to know how many moles that we would produce of this guy. First off, the one way that we know it is a limiting reagent problem is really this right here. Either we are given the moles of each reactant or we're given some piece of information that allow us to calculate the moles of each reactant. So that's how you know it is a limiting reagent problem rather than a basic stoichiometry problem. You have enough information basically to get to the moles of each reactant. That definitely is like, I need to figure out the limiting reagent. So that is the key there, enough information to calculate the moles of each reactant. And once again, that is really the key trigger to, I should definitely figure out which one's the limiting reagent. The way that we did it here is really you do follow sort of the same 4 steps as we just talked about. The additional sort of difference is right around here, you need to figure out which one is the limiting reagent. The reason we do need to figure out which one's the limiting reagent is because once it gets used up, the limiting reagent, there is no way you can make any more product. So it is always the limiting reagent that determines how much product that you're able to form. And that's why it's always important to figure out which one's the limiting reagent. By the way, a reminder that the limiting reagent is not always going to be the one with the smaller number of moles. You actually have to do a calculation to figure it out. Sometimes people just go, well, this one has a smaller number of moles, so it will be it. It will not always be that based on the numbers and coefficients that you have. So you should always do a calculation. So one of the 2 ways that we talked about, the official way, I think that I taught it to you this semester, if I'm not mistaken, is you really can take either one of the reactants. So for example, if we already converted to moles and these are our starting moles of each of these guys, we could do a very simple stoichiometry calculation where we calculate if I want to use up all of one of my reactants, how much of the other one do I need to toss in there? So for example, I would figure out here how much I need of B to use up all of A. In my made up example, I would start with my starting amount of A, moles of A. Going from the equation, it is a 2-to-1 relationship, which means for every 2 moles of A, I get out there 1 mole of B, which means I end up with 2.5 moles of B would be needed in this case. This calculation that I just did here is basically just to figure out which one's the limiting reagent. So I need 2.5 moles of B. If I look up in my made up example here, I actually only have 2 moles of B. I do not have enough, which means in this case, B would be my limiting reagent and A would be my excess reagents. At this point, what I would want to do is once I determine that, go back to my limiting reagent and a starting amount, which would be B. I then could do my mole to mole relationship between the limiting reagent and the product. And in this case, it is a 1 mole of B gives me 2 moles of AB. And that means that I would get 4 moles of AB would be produced in this reaction. Obviously, if I knew what A and B were in terms of their molar mass, I could figure out how many grams that would be. But this is what is referred to, obviously, as the theoretical yield. This would be the theoretical yield in moles. And again, we can calculate to grams at that point. So this is one approach where it's basically the same 4 steps. Just you kind of do this little calculation in between. You could do either one of the reactions to do that. The other approach is simply do 2 separate stoichiometry calculations. One starting with the first reactant and figure out how much product it produces. One with the second reactant and figure out how much product it produces. Whichever one produces the smaller number of grams is both your limiting reagent and your theoretical yield. So that's the other approach, just kind of 2 separate calculations. And whichever one is the smaller number is both the limiting reagent and your theoretical yield. Question on limiting reagent problems. We also could go back once we figure out which one is our excess reagent. We could also go back and do a calculation to figure out how much of the excess reagent would be left over. Again, that's a common sort of question that's sometimes asked. Question on stoichiometry, limiting reagent stoichiometry. We, I think, sort of finished up also talking about percent yield, right? And percent yield is the actual yield divided by the theoretical yield times 100%. So a lot of times when we do stoichiometry problems, we oftentimes will calculate our percent yield. Remember, close to 100 is good. Small percent yield, bad. Yes. Unhappy face, happy face. Remember that even though it may seem like a good thing, over 100% yield, also not a happy face. Yeah, because that usually means, yeah, kind of screwed up there along the way. So remember that the theoretical yield really is the maximum yield that you could get. It is the one that is calculated from the equation. That is your max yield. Calculated from the equation. And what you start with. The actual yield is pretty much what it sounds like, what you get when you do the experiment. That is usually given to you in a textbook problem. So your actual yield is usually the one that's given to you. Your theoretical yield is usually one that you need to calculate. And then obviously you divide the two and times it by 100 would give you your percent yield. Any questions on that there? Okay, so I think that is chapter 9, pretty much. We then rolled to chapter 13, which should be fresh here since it's recent stuff. Chapter 13 was all about gases and everybody's favorite thing. So gases and gas laws and all that good stuff. Remember, 3 different types of units. This is an atom. That is a torr, and that is a millimeter of mercury. And that is 760 millimeters of mercury, which means 760 is your magical number to do conversions, right? And obviously, if we have atmospheres and want torr or millimeters of mercury, we're going to multiply by 760. And if we have torr or millimeters of mercury and we want atmospheres, we will divide by 760. And that really is because a millimeter of mercury is the same thing basically as a torr. It is a one-to-one relationship between those two. Pretty much there are gas molecules basically flying around, right? When we get to the gas stage, and as they are flying around, there's a number of collisions that occur with the container. And it is those collisions that cause the pressure that we associate with gases. Obviously, the increase in the number of collisions means an increase in pressure, and vice versa, a decrease in pressure as we go down as well. So we talked about several gas laws. Most gas laws involve three variables: pressure, volume, and temperature. So we started with our friend Boyle. And Boyle had a relationship of P1 V1 is equal to P2 V2. This is at constant temperature. And what he saw was, again, as the pressure increases, the volume decreases. So as one goes up, the other one comes down, and vice versa, obviously, here. Again, you can think of it in a smaller volume. There's a lot less room for gas molecules to fly around in, which means we would have a greater number of collisions and a higher pressure. A larger volume would give everybody a lot more room to fly around in, lowering the number of collisions and also lowering the pressure. We had our friend Charles' law, which is V1 T1 is equal to V2 T2. This is at constant pressure. And as we talked about with Charles' law, the way it's able to really maintain constant pressure is actually the volume changes. So the volume basically adjusts with the pressure or with the temperature. So as the temperature increases, so does the volume. And what that does is, because the volume increases, the temperature increase is going to cause the gas molecules to fly around faster, causing more collisions. So the increase in the volume will allow the number of collisions to still remain pretty constant, and that keeps the pressure constant. Vice versa, if you lower the temperature, your gas molecules should start to fly around a lot slower, which means you'll have less collisions, and you'll see the pressure would start to drop. But to make sure the pressure doesn't drop, what happens is volume gets smaller, allows more collisions to really keep, not really more, it's really the same by that smaller volume, and that's how it keeps the pressure constant. Important not only in this gas law, but pretty much all gas law, is the idea here, what they saw with Charles' law, which was you could graph volume versus temperature. And for any gas that you like, you can take it back to the temperature axis, and it will always hit minus 273.15 degrees Celsius, which is our friend Kelvin basically recognized. So pretty much every gas law, temperature needs to be in Kelvin. So that's the temperature in Celsius plus a 273 will give you that temperature in Kelvin. Remember, even problems where they ask for it in degrees Celsius, give it to you in degrees Celsius, you got to convert it to Kelvin, put it into gas law, and then unconvert it afterwards. A similar gas law is Guy-Lussac's law, and that's like P1 T1 is equal to P2 T2. This would be at constant volume. Different in this case is the volume will not change. So it's fixed or rigid, which means when you do increase the temperature in this move, there is no choice, but you will see the pressure start to rise because the volume will not adjust to help out. And vice versa, if you lower the temperature, you will see the pressure start to decrease, again, because the volume is fixed, it's not going to help out. And again, obviously here, we need some Kelvin there on our temperature. We also had our friend Avogadro. He had a law as well, and his was V1 N1 is equal to V2 N2. This was actually at constant pressure and temperature. And at constant pressure and temperature, with Avogadro's law, basically the number of moles and the volume of the gas basically change pretty much proportionally to each other. And that's what N stands for here. Those are moles, basically. And V is volume. Now, in all these sort of formulas here, there's kind of a before and after sort of condition. And it really, in terms of units, doesn't really matter except for temperature. But as long as all the other units are the same units. So what I mean by that, obviously, if the two pressures could be any pressure unit as long as they're the same. Volumes could be any volume unit as long as they're the same. But again, the temperature does need to be in Kelvin. Taking all these sort of formulas together gives us the ideal gas law. And the ideal gas law is our PV equals nRT. So this is a little bit different. It is obviously one pressure, one temperature, one volume. It is also the most restrictive in terms of units. Pressure here needs to be in atmospheres. Volume needs to be in liters. N should be in moles. And temperature should be in Kelvin. And the reason for all that is the value of the gas constant. R is 0.08206 liters atmosphere Kelvin mole. Some people use the rounded version, 0.0821. It's all good if you want to use that one. The good news about that is, if you remember R there and the units to go with it, it'll tell you what everybody else's units need to be. But an ideal gas, right, which is what this is here. Now, an ideal gas is really a gas that we really deal with in most cases, and we sort of consider most things a ideal gas. An ideal gas, really two things that make something sort of an ideal gas is the idea that the volume of the gas itself under normal pressures and temperatures is pretty much zero. It's very, very small compared to the container at which they're flying around in. So that's why in most problems that deal with sort of ideal gases, they oftentimes will talk about the volume of the container as being the volume for the gas, because its volume is more significant than the volume of the gas itself. The other really major thing that makes something an ideal gas is the idea that an ideal situation, although you have multiple different types of gas molecules flying around in the same container, in an ideal situation, they basically will not interact with one another. So there's no attractive force between different gas molecules. There's no repulsive forces between different gas molecules. It's almost like those gas molecules are in that container by themselves. And that's sort of the ideal situation. And that's why we use something like the ideal gas law. We didn't talk really a lot about real gases in here, but in 1A, you'll talk about real gases, where you use sort of the scary version of the ideal gas law there, and a lot more things added to it. But in most cases, we use sort of the ideal gas law for those type of situations. There's a couple other important sort of things here we talked about at this point. That was STP, which is standard temperature and pressure. And remember that that actually does have values. That is a temperature of 273 Kelvin and a pressure of 1 atmosphere. Obviously, it's converted equivalents. And there is a relationship that if it is at STP and only at STP, 1 mole of any gas will equal 22.414 liters. So this is a conversion that you could use at STP conditions, and it would allow you to perhaps bypass using the ideal gas law. If you're not sure you should use it, then definitely use the ideal gas law, because you can use the ideal gas law in any conditions, STP conditions, non-STP conditions, but you definitely can only use that conversion if it's STP. So if the pressure is not 270, not 1 atmosphere, and the temperature is not 273, you definitely should not use that. Any question on those there? We also talked about one more here, which is sometimes referred to as the combined gas law. And it really is sort of based off of the ideal gas law, P1 V1 over T1 equals P2 V2 over T2. Once again, here our temperature needs to be in Kelvin. The nice thing about this one, as we talked about, is it's because it's really sort of based off the ideal gas law, you actually can remember this version of it. And again, you pretty much could just scratch out anything that is constant or not given to you. So again, if you weren't given anything about moles or temperature is constant, you could just scratch those out and you have Boyle's law, as we talked about. You know, if you have no pressure or moles given to you, you can scratch it out, and now you have Charles' law. So that's a good one to sort of remember. Just take out whatever is constant or not given to you, and you'll probably have the appropriate gas law that you need, which, as we talked about when we were going through this chapter, pretty much, you know, if you remember this one and you write it correctly, that'd be good. And the ideal gas law, you know, you'll probably be in good shape for any gas law that you might need. Again, just taking out the constant ones and the one on top and just using the ideal gas law where it's appropriate. Obviously, the ideal gas law is a one and done situation, one pressure, one temperature, one volume. Obviously, the top one there are sort of like a before and after situation that you would want to use that. Any question on that there? In addition, in this chapter, we talked about partial pressures. So we talked about partial pressures. And partial pressures really occur when we have a mixture of gases. And in a container where we have, you know, gas molecule A, gas molecule B, gas molecule C, however many, obviously they're all flying around. They're all causing collisions, which means the total pressure here would be a result of the pressure of each of those gases in that mixture. And that's why these are referred to as partial pressures, because they each are partially contributing to the overall pressure of that mixture. So there's really a couple kind of different partial pressure situations we talked about. One is just, frankly, you're given information about two gases that are flying around in the same container. Because they're flying around the same container, for example, here, we could calculate each of the partial pressures by using the ideal gas law. And because they are in the same container, they will have the same temperature. They will also have the same volume. So really the only thing that's different for each of them is the number of moles. So what you would do is simply solve the ideal gas law here for each gas separately, making sure everybody's in the correct units. And once you have that, you could then calculate the total pressure by just simply taking all three of those partial values you calculated and basically just adding them together. So that would give you your total pressure. So that's a very common sort of partial pressure problem where things are flying around. Another situation that we talked about where partial pressures come into play is like in the lab, and how you did a couple experiments and how gases are sometimes collected and very commonly collected, which is they are collected over water, are saturated with water vapor. So these are two very common sort of ways, which is basically the same way. And that is like you did an experiment, you know, when you think and you did your little magnesium and your HCl came down. And as that reaction sort of occurred, basically you bubbled up some hydrogen gas. And at the end of the experiment, you had a spot there where you had your hydrogen gas. Obviously, the water exited as well. But during the process of that reaction occurring in water, the heat from the reaction is also going to evaporate off some of the water. And in addition to the hydrogen gas, which is really what you're interested in, you got yourself some water vapor that came in there. And if you were doing some type of calculations like we did in lab and certain book problems, you're really not interested in the water's vapor pressure contribution. So we usually will have to do some type of correction calculation where the total pressure would equal the pressure of the gas you're interested in plus the vapor pressure of water. Usually the vapor pressure of water is a table value that you look up on the table. Like in lab, they have it still hanging there on the board, I think, still to this day, over there on the right. So you went there, looked it up with your temperature, and you found the vapor pressure of water. Now, what this basically becomes is really just a subtraction problem, because in this case, you're interested really in just the pressure of the gas. So the pressure of the gas you're interested in would be the total pressure minus the vapor pressure of water. This is usually your atmospheric pressure or your barometer reading, and you're basically doing a correction calculation here to get really the pressure of just the gas by itself, sometimes referred to as the pressure of the dry gas, because you subtracted off the basically vapor pressure of water in that case. So that's another common sort of gas situation that occurs in a partial pressure situation as well. Any questions on that there? That is 13. Then we're responsible for chapter 14 dealt. And see what was in that chapter there. So basically we have our 3 phases that we talk about. Very dense and rigid. We also have our liquid phase, where things are still relatively packed in tight to one another, but there's obviously a little bit more room for movement, which is why liquids are fluid. Our gas is completely broken apart from one another and flying around, causing pressure. Positions that we talked about, which is solid to liquid, which is the process of melting. There is a liquid to solid, which is the process of freezing. Liquid to gas, which is evaporation or vaporization. Going from gas back to liquid is condensation. Going from solid, skipping liquid to gas is sublimation. Going from gas, skipping liquid back to solid is deposition. Now, before I get too far into 14, we also talked about, obviously, in chapter 13 with gases, stoichiometry involving gases. And again, a reminder that really is the same clause somewhere along the way. So back to this here. In terms of energy, as we go from solid to liquid to gas, those are all endothermic processes, which means heat and energy is absorbed. You need to put heat and energy in to do that. As you go from gas to liquid to solid, those are all exothermic processes where heat and energy needs to be released. A reminder that when we talk about endothermic and exothermic and energy, typically endothermic values are positive values, right? In terms of values for energy, exothermic values are negative for energy. So again, if you have some type of energy value given to you that's negative, you know that process overall is exothermic. And if you have one that is endothermic, it will be a positive value. So this also occurs, these transitions occur at the same temperature. So melting and freezing occurs at the same temperature. That is the normal freezing or melting point of a substance. Same thing here, evaporation and condensation also occur at the same temperature. That is the normal boiling point of a substance, is where you have that. So when we have transitions of, or changes in transitions, like if we look at something like water here, we have something like this. And we say down here is ice, and this would be liquid water, and this would be like steam, which is obviously the gas version of water. So those transitions that we're talking about occur, very badly drawn here, but I'll level it out there. There we go. For example, for water, that would be 0 degrees Celsius. Up here, that transition between liquid and gas occurs at 100 degrees Celsius. So really, this is our solid phase, this is our liquid phase, and this is our gas phase here. Now, there's a certain amount of energy required to simply change the substance from one phase to the next, not really changing this temperature. So at 0 degrees Celsius, when we talk about water, we basically have both phases in equilibrium with each other. We have ice, some liquid water sort of happening. Not until you get a little bit above 0 degrees Celsius that you got liquid water, not until a little below 0 degrees Celsius that you have ice, but right at 0 degrees, they're in equilibrium with each other. Same thing when you get to 100 degrees Celsius, you have basically some liquid water and you got some steam or water vapor sort of happening at the same time. And again, to get above 100 degrees Celsius, you really have steam. A little bit below 100, there is really liquid water. So the amount of energy required to do those changes, or what are sometimes referred to as the heat of fusion and the heat of vaporization. The heat of fusion, or the delta H of fusion, is the amount of energy required to do nothing more than take a substance from the solid phase to the liquid phase, or the liquid phase back to the solid phase, whichever way you want to go, not change the temperature. So for example, the delta H of fusion for water is about 335 joules per gram. That means if I wanted to take water at 0 degrees Celsius from ice at 0 degrees Celsius to liquid water at 0 degrees Celsius, that will require a positive value of 335 joules per gram to do so. It is positive because we're putting energy in, it is endothermic. If I wanted to take liquid water at 0 degrees Celsius to ice at 0 degrees Celsius, that will require minus 335 joules per gram to do so. It is the exact same number, just the sign is different depending on whether the process is exothermic or endothermic, and negative being exothermic is why we do in that particular case. Same thing up here. This is the delta H of vaporization is referred to, or the heat of vaporization. And same idea. So for example, the delta H of vaporization for water, roughly 2260 joules per gram. So same idea. If at 100 degrees Celsius, I want to take liquid water to steam at 100 degrees Celsius, that's an endothermic process. I would have to put in there positive 2260 joules per gram. If at 100 degrees Celsius, I started with steam, and I want to go to 100 degrees Celsius liquid water, I would take out minus 2260 joules per gram. So once again, it's the exact same number, but the sign is different to do so. Any questions on that there? So we also see that it takes a lot more energy, if we use water as an example, to do the transition from liquid to gas and gas back to liquid. Because as we go from liquid to gas, we're completely breaking apart everybody, right? They have to break all those bonds to get away from each other. It takes a lot more energy to do so. Then as we go from solid to liquid, where they're still pretty much near each other, they haven't like completely separated from one another. So it takes less energy to do so. So if you wanted to take something on this is what is referred to as a heating curve going in this direction, heating going that way, and cooling curve going basically in the opposite direction. So if we were to calculate something going from, say, one phase to the next without changing the temperature, but just changing the phase, you should be using a heat of fusion or heat of vaporization, depending on which phases you're moving. If you're moving anywhere on this curve where you're actually in the same phase, but you change temperature, like for example, that red spot there, this red all the way there, and this red, all those red part of the curve are the areas where we're actually staying in the same phase, but we're changing the wanted the heat for that. That is our friend specific heat. Q is equal to ms delta T. So we would use the specific heat equation to do that, where Q is the heat or energy, and M is the mass, S is the specific heat capacity, and T is the change in temperature, which should always be, as we talked about, final minus initial, as that is the one thing that will really give you the negative sign or not as to whether or not you do have it. Specific heat capacity, remember, for water or liquid water is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. A reminder that the specific heat capacity does change with the phase. So if you're doing this transition here, from say -5 degrees to like 0 degrees Celsius, you would need the specific heat capacity for ice, non-liquid water. It'd be a different number, like 2 rather than 4. Same thing if you're up here doing like a transition like 100 degrees Celsius to 105 degrees Celsius, you would need the specific heat capacity for steam, or the gas version of water, which also would be about 2.01. But they're different numbers. So it's not always going to be the 4.184 unless it is liquid water. Well, that's also a reminder how you convert, right, between joules and calories, which is a very common conversion. There's 4.184 joules is equal to 1 calorie, and that also is used. So if we were to do some type of problem where we want to know how much energy it would take if we started down here, say at -5 degrees Celsius, and took it all the way up here to like 105 degrees Celsius water, there's really that occur different calculations that you would need to do. You would need to first do basically this part here, where we would take it from -5 degrees Celsius to 0 degrees ice. You then would have to do the phase change, which would involve the heat of fusion calculation. You then would do a specific heat calculation from 100 degrees Celsius to 0 degrees Celsius liquid water. You would have one more phase change coming this way using the heat of vaporization, and one last specific heat calculation going from 100 degrees to 105 degrees Celsius. And if you wanted the total amount of energy, I lost track of how many I just did there, but that's 1 step, 2 steps, 3 steps, 4 steps, 5 calculations you would do. The total amount of energy would be found by just adding all the steps together. So to find the total amount of energy, you would just add 1 plus 2 plus 3 plus 4 plus all 5 steps basically together, and that will give you the total amount of energy required to do that. That would all be endothermic. As I would did that example, I should end up with a positive number. If I started at the top at 105 degrees Celsius and wanted to take it all the way down to ice at -5 degrees Celsius, the only difference is everybody would be negative. Yeah. And the end result would be the exact same number, except that would be negative because that's all exothermic processes that occur. So in a situation like that, you got to kind of do it kind of step by step and add each of those together. And you could do that because energy is a state function, which means it doesn't matter how long it takes you to get there. What matters is where you start and where you end. And all the pieces basically are additive in that case. Any questions on chapter 14 there? Okay, I think we'll lay